Hi guys, this is Dr. Manjunath Chennapur from Anveshana Academy, Bangalore, India. Dear students, in the previous class we discussed one numerical on Otto cycle. With one method I have done that calculations. Today I am going to solve the same numericals with other method. So numerical on Otto cycle. The topic is numerical on Otto cycle. We are discussing first numerical. That numerical solved with one method. With help of another method, we can solve the same numericals. Now, what is the another method? With the help of work done to stroke volume, that is mean effective pressure. So, with help of work done, so we know already, dear students, efficiency generally we know work done to the heat supplied or heat addition. Efficiency of an engine is equal to work done to the heat supplied. With the help of work done equation, I can calculate the mean effective pressure. How to calculate the work done here now? So therefore you can say now the simple method, work done is equal to efficiency into heat addition. Some authors they will take QS or some authors they will take QA. With the help of this equation, with the help of work done, I can calculate the MEP. Once you know the value of work done, you can easily calculate the mean effective pressure, that is WD divided by work done divided by stroke volume, that is V1 minus V2. So we can calculate the work done with help of this equation. How to calculate? The previous problem that we will do with help of this equation now. So dear students, once again I will read the problem. An engine of 250 mm bore and 375 mm stroke works on a constant volume V equal to constant for both heat addition and heat rejection, heat supplied and heat rejection, that is the Otto cycle. Full stop. The clearance volume is 0.00263 meter cube. The initial pressure and temperature are 1 bar and 50 degrees Celsius. If maximum pressure is 25 bar, find first one air standard efficiency of a cycle, second one mean effective pressure. So when it comes to constant volume cycle, that is nothing but what? Otto cycle. So for Otto cycle, what I have done here now, I will draw the PV diagram and TS diagram. Okay, so pressure versus pressure variations with volume is PV diagram, temperature variations with entropy is TS diagram. So as I told, there are four processes in the Otto cycle. 1 to 2 adiabatic compressions, 2 to 3 heat addition, 3 to 4 adiabatic expansion, 4 to 1 heat rejection. These are the 4 points where 4 processes we are having. Okay, this all we have discussed now. When it comes to this thing data, he has given some engine bore diameter is equal to 250 mm, that is he has given, that is D equal to 0.25 meter he has given, that I have taken, and stroke length he has given 375. Stroke length he has given 375 mm he has given, so that is L equal to 0.375 meter. So that I have listed now. Initial condition, then when it is a BDC TDC, it is having in a volume, that volume we can call it as a swept volume, and the volume which is occupied by the air fuel mixture from point BDC to TDC swept volume, the distance we can call it as a stroke length, that is L. Okay, the volume which is occupied from TDC to the cylinder head, that we can call it as a clearance volume. The summation of clearance volume and swept volume, we are going to get one more volume, that we can call it as a total volume. The total volume is Vs plus Vc. Okay, so he has given now Vc, he has given here now, that is 0.00263 meter cube he has given. And when the piston is at BDC, you can name it as a 0.1 and you can call it as a 0.2. When it is a piston is at 0.1, he has given some conditions now. What is the P1? P1 is equal to how much he has given? 1 bar he has given. Then temperature he has given, that is temperature at 0.1 or initial condition is 50 degree Celsius he has given. You can convert it into Kelvin by adding 273. Okay, so fine. Next, P1 and T1. Next, he has given when it reaches adiabatic compression, right? At that moment, where he is going to, we are going to add the heat. Actually, we are going to supply heat. That heat addition may be QS or QA. You can take. When you added heat, right, the pressure of the gas increased to maximum. That means what? point 3, that pressure at point 3 we can mark it as a P3. The maximum pressure is 25 bar he has given. But dear students, one thing you have to remember here now, but T2 is not given. Okay, T2 is not given, T3 is not given, and also we can see P2 also he is not at all given here now. That data we can calculate with help of pressure ratio. This is the problem. Already the same previous problem we know already. This is same previous problem, but I am doing it with another method. It's an Otto cycle, same problem. Okay, I will go to the next step now. So what are the things new? First, what is the first step? You have to list out the given data. What are the given data? Bore is equal to 250 mm he has given. Convert it into meter, that is 0.25 meter. Then stroke length he has given 375 mm. Convert it into meter, that is 0.375 meter. Clearance volume he has given, that you can mark it as a VC, is equal to 0.00263 meter cube. Initial pressure he has given, as I told, that is 1 bar. You can express that same thing you can in terms of Pascal as 100 kilopascal. Initial temperature is 50 degrees Celsius. Add 273, then you will get 323 as a Kelvin. Okay, maximum pressure he has given 25 bar. Then we can express same thing in kilopascal as 22,500 kilopascal. These are the given data. Now what to do this now? What you have to do here now? You have to solve the problem step by step. What is the first step now? You have to calculate the swept volume. Second step, you need to calculate the compression ratio. Third step, you need to calculate the efficiency of the engine, Otto cycle engine, Otto engine or Otto cycle. Then what is the temperature at the end of the compression? At the end of the compression, that is T2 as I told. Then heat addition you need to calculate. What is the QS, or you can take QA also, heat addition. Next, what is the work done? Okay, then after that you can calculate the mean effective pressure, mean effective MEP. These are the steps we need to follow now. First one, what I will do, I will go with the first one. What is that? First one, you can see here. First one, swept volume calculations now. So here now, first there are two important parameters as I told. Here there are two findings. One is efficiency of the air standard cycle, that is neta air. Second one, I need to calculate the mean effective pressure, PMEP, or some authors they will take PM also. We need to calculate now. So first what I will do, I will go with what air standard efficiency, that is first parameter, air standard efficiency. In that we need to calculate some other parameters which are required to calculate the air standard efficiency. In that first parameter is swept volume. There, what is the swept volume? You can see here, dear students. To calculate swept volume, as I told, this is what diameter, bore diameter capital D, and it is having a distance. The piston moved from BDC to TDC, that distance we can call it as a stroke length. With help of that stroke length we can calculate the swept volume. What is the swept volume? Vs is equal to cylindrical object, right? 5/4 into D square into L. The same formula I am going to use it here. Vs is equal to 5/4 into D square into L. 5/4 is the constant, I will keep it as it is, into D. What is D? 0.25 meter square, 0.025 meter square into L, 0.375. Multiply, you are going to get a Okay, you are going to get swept volume as Vs is equal to, the final answer, do substitution. So we are going to get a 0.018 meter cube. Okay, what is that? You can substitute the values now. So what I can do here now, 5, where is the 5 value? 5 by 4 5/4 into 5/4 into 0.25 square into 0.375 equal to, how much you got? 0.018 meter cube. That's answer you got. Okay, now you got this clearance volume now. So with help of this clearance volume, what I can do, I can calculate the compression ratio now. What is compression ratio? That I already told, dear students. R is equal to total volume to the clearance volume. What is total volume? Total volume is nothing but what? It's a combination of swept volume plus clearance volume. That is what? Vs plus Vc divided by Vc. What is Vs now? Vs is already given. Vs already has given, sorry, Vs already we calculated as a 0.0018, 4 meter cube, plus Vc he has given in the problem itself, that is 0.00263. Again divided by Vc, you do simplification, you will get R as 8 meter, sorry, R as a 8. You will get R as a 8. But here, dear students, when it is a R, right, then volume, it is total volume, Vt, right, total volume by clearance volume, right, clearance volume. So what is the unit of total volume? That is meter cube. Volume of clearance volume, meter cube. Hence meter cube get cancelled. Hence we are not having unit for the compression ratio. So therefore compression ratio is equal to 8. So that second calculations you done in the air standard efficiency. Next, third one what you have to do now, because our aim is to calculate the air standard efficiency, right? To calculate air standard efficiency, the sub parameters are very important. What are those? Vs and R. We calculated. With the help of this, what I can do, I can calculate the air standard efficiency. How it is, that we can see here, dear students, now. Now, so we know the equation, right? What is the efficiency equation? Neta is equal to, just a minute, neta of air or Otto is equal to 1 minus 1 divided by 1 minus into bracket 1 divided by R to the 4 of what? Gamma minus 1. This is the formula we are having now. Fine. What is the value of gamma for air? That is 1.4. Specific heat ratio, that is 1.4. Now what I will do now? I will substitute this value now. To calculate the air standard efficiency, I require two value here now. One is R, that is compression ratio. Another one is gamma. Gamma is the constant that we know already, 1.4. Then we have already calculated R value that we got as a 8 actually. Then I will substitute all value here now. So neta is equal to 1 minus 1 divided by R is 8. I have substituted. Then 1.4 gamma value I have substituted. Next minus 1. Then what I will do? We are going to get the value here now. So then neta is equal to 1 minus 1 divided by 8 to the 4 of what? 1.4 minus 1, we are going to get a 0.4. Now neta is equal to 1 minus 1 divided by this value is 2.297. Now do simplification of this now. Now 1 divided by 1 minus, you will get it now. 1 minus this much. Then we are going to get a 0.565. That is a neta value. Then multiply with 100. Then we are going to get neta is equal to 56.5% as the efficiency. That means what? Otto cycle efficiency, or we can call it air standard efficiency. The first parameter is done now. Now, so what we can say? We can say that first parameter efficiency is done now. Now I will move towards second parameter, mean effective pressure. That we can do in another method, as I told. That we will try now. So second parameter is what? Mean effective pressure. To calculate mean effective pressure, as I told, we are having an equation now. What is that equation? Mean effective pressure is equal to total work per one cycle to the swept volume. This is the formula now. What is total work? How to calculate the total work? I will tell now. So to calculate total work, we know already equation. So general equation we know. Okay, just a minute. Okay, 1 minute. Okay, we know already efficiency is equal to what? Output to the input. Output from engine is what? Work actually. Input is what? Heat supplied or heat added, we can call. Okay, so work done. So how to calculate this work done? So work done can be calculated as, if you know the efficiency into what? Heat addition. But already we calculated efficiency as a 56.5%, but you don't know the value of QS. So heat addition, that heat addition we can calculate at a constant volume. For that we are having an equation. What is that? QA is equal to M into per kg M into CV into highest temperature minus lowest temperature. That we are having an equation that you can see here now. With help of that equation I can calculate the heat addition. Once you know the value of efficiency and heat addition, you can calculate the work done. Once you know the value of work done, you can calculate the mean effective pressure. But to calculate the mean effective pressure, we required heat addition. To calculate that heat addition, we required the value of what? T3 and T2. So we require the value of what? T3 and T2. That T3 and T2 we need to calculate. Then how to calculate the T3 and T2? That we can see here, dear students. So to calculate heat addition, we require the value of what? T3 and T2. That T2 and T3 can be calculated with help of a temperature ratio now. What is the temperature ratio that you can see here, dear students? Okay, so T2 by T1. First I will try to calculate the temperature at the end of the compression, that is T2, because T1 E is already given. So that you can see here, dear students. So T1 he has already given 50 degrees Celsius, but T2 is not given, P2 is not given. P2 and T2 I will try to calculate with the help of a temperature ratio and pressure ratio of an Otto cycle now. What is that? So T2 by T1 I am having an equation. T2 by T1 is equal to R to the power of what? Gamma minus 1. So what I will do, with the help of this relation I will try to take the value of T2. So therefore T2 is equal to T1 into R to the power of gamma minus 1. What is T1? We know already in terms of Kelvin, that is 323 Kelvin, into what is R value? That is 8. Gamma minus, that is 1.4 minus 1, we are going to get 0.4. So therefore T2, you will get it as a T2, do calculations, simplify it, and you are going to get the value as value of T2 as 741.9 Kelvin. Now you know the value of T2. So similarly what I will do, I will try to calculate the value of what? T3 at point T3 also it is not there. T3 I will try to calculate that when we are adding heat addition, when we are adding heat rate at a constant volume. So that means, so temperature at the, no, that can be calculated with the help of this equation. P3 by T3 is equal to P2 by T2. That is why it's so, it is a constant volume process. When it constant volume process, we are having a relation, that is P3 by T3 is equal to P2 by T2. Now I will do a modification in this equation. As per my equation, I want the value of what? P2. So therefore P2 is equal to, but P2 a constant volume process, right? We have one more equation. P2 can be calculated. P2, I am using this equation later, but P2 I can calculate with the help of one more equation. What is that? P2 is equal to P1 into gamma into R to the power of gamma. So then I will substitute now. P1 already I know 1 bar. Then RC value R compression ratio already calculated, that is 8. Then gamma 1.4. With the help of this relation, I will calculate the value of P2. That is 18.37 bar now. Now once you know the value of P2, with the help of this relation, I can calculate the value of what? T3, because here P2 is unknown. P2 can be calculated with the help of this relation. That I have done. Then now I will modify this equation. T3 is equal to P3 into T2 divided by P2. So therefore T3 is equal to, I will take T3 out. T3 is equal to P3 into T2 divided by P2. So therefore what I will do now? I will substitute all the values what I know already. T3 is equal to P3 he has already given, that is 25 bar, into T2 is already we have calculated, that is 741.9 Kelvin. That substitute divided by what is P2? P2 is already we calculated, right? That is 18.37 bar. Now I am putting all values in terms of bar only. Okay, I will put all values in bar. Then what I will do now? Bar will get cancelled. Here at the denominator bar will get cancelled. Then only thing temperature is going to get. That temperature is what? T3. That means what? 1010. That means, dear students, T3 is greater than T2. That means what? At T3 you are going to get maximum pressure and temperature as per the as per the Otto cycle, that you can see here now. When it comes to at point 3, that you can see here now, you are going to get maximum temperature and maximum pressure. This is what? Maximum pressure. When we comes to TS diagram, when we are going to draw a line, right, then we are going to get a maximum temperature. So at point 3 we are going to get maximum temperature and pressure. That we can see it. Here now. Maximum temperature also you got. Maximum pressure is 25 bar. Okay. Now we know the value of T3 and T2. All values you have calculated now. Now you are adding heat at point 1 to 2, right? You are adding heat. You can see here now. You are adding heat at 2 to 3. When we are adding heat at 2 to 3, that heat addition, you can write now. Heat addition, you can QA is equal to M into CV into highest temperature is T3 minus T2. I can calculate the heat addition with the help of this equation. If you are calculating the heat addition per kg, then M equal to 1. You can neglect that. Then CV is the specific heat at constant volume, that you can see here now. That same formula I am using here now. So therefore heat addition is equal to QA is equal to CV. As I have taken M is equal to 1. CV into T3 minus T. CV, that is specific volume for specific heat at constant volume. That too for air is 0.1. 718 kilojoules per kg Kelvin, that is a constant. Now I know the value of this also for air, because the given air fluid media is air actually. Now I know the value of Cv. Then T3, T2 already calculated. Substitute all values now here now. So Cv is equal to this much, T3 is equal to this much, T2 is equal to this much. You already calculated. Do simplification. We are going to get heat addition as 192.89 kilojoules per kg. Now you got the heat addition. Once you know the value of heat addition, then what you can do now? You can calculate the efficiency, right? You can calculate the efficiency. We know the equation to calculate the efficiency. What is that? Efficiency generally, you can, efficiency is equal to work done by heat addition. Sorry, efficiency is equal to, sorry, 1 minute. That is heat addition, QA. So therefore work is equal to neta into QA. The same thing I have written it. So therefore work is equal to neta into QA. So now what is neta? Already you calculated, that is 0.56.5%, that is 0.565 into what is the heat addition, that also you got it. Now you got the total work done here now. That is how much? 109 kilojoules per kg. Work done, you got it. So now we can calculate the mean effective pressure. How to calculate the mean effective pressure? That is the ratio of work done to the swept volume. Dear students, you have to see here now, mass of air you supplied per cycle. Now this is one cycle, right? This is one cycle, 1 to 2, 2 to 3, 3 to 4, 4 to 1. One cycle. At one cycle, how much work you are getting, that you need to consider here now. So if I want to calculate the mean effective pressure, work done per one cycle to the swept volume. Swept volume already you calculated, but you need to calculate work done per cycle. You need to calculate work done per cycle. You need to calculate. How to calculate that now? That means what? You are supplying certain amount of air, right? How much amount of air you have supplied, that you need to calculate first. How much amount of air can be air you have supplied to the engine, that is mass of air is equal to P1 V1 RT1, because I am using ideal gas law here now. PV is equal to what? MRT. So if I want M value, what I will do now? M is equal to PV divided by RT. The same thing I am going to apply it per condition 1, P1 V1 RT1. So the same thing. What is P1 in terms of kilopascal? You put it, or else you can put it kilopascal, because all values we are going to get it in terms of kilopascal, kilo. Okay, P1 V1. Next, R is the ideal radial gas constant, that is 0.287. Next, T1 you already know. Do simplification, then you will, how much amount of mass you supplied, mass of air you are going to get now. That mass of air you multiply with the total work, then only you are going to get a work done per cycle. So work done per cycle is nothing but what? Total work done per cycle is nothing but what? Work done per cycle is equal to total work multiplied with what? Air supplied in one cycle, that to how much? This much amount of air only you are supplying, 0.0225 kg. When multiply, you are going to get 2.445 kilojoules of work done you are getting per cycle. But this represents a total work done. All cycles you can consider n number of 200 cycles, 400 cycle, 500 cycle. That is the total work done. Okay, but here work done per cycle, for that I can calculate it with help of considering mass applied air, mass of air. Then work done per cycle I calculated as 2.45 kilojoules. Then what is mean effective pressure now? So therefore mean effective pressure is equal to work done per total work done per work done per one cycle divided by Vs. Work done per cycle is equal to how much? 2.45 kilojoules divided by 0.0. Vs value already calculate 0.0 something. You substitute it, you will get it in terms of kilopascal. Then 10 to the power of 5. Then you will get what you will get? Mean effective pressure as a 1.33 bar. So dear students, this is how to calculate the mean effective pressure with the help of a work done equation. So the final answers are what? 56 point, efficiency is 56.5%. The mean effective pressure which is acting on the piston, mean effective pressure is mean effective pressure is equal to 1.3 bar. So this is what? So efficiency is 56.5%. Then mean effective pressure is 1.33. It is not percent, it is 33 bar. Okay, so this is how to solve the numerical. Dear students, here I request you, please do subscribe my channel, comment, and share my videos. Please support me to make more and more videos for different subjects too. We'll continue next class. Thank you.